Hey everyone, welcome back. I hope you're all doing great. In this video, you'll learn how to calculate float time, also known as slack, and how to identify critical activities in the critical path. This is an important step in scheduling, as it shows you how critical or flexible each activity is. Alright, let's start with calculating float, which is also known as slack. There are different types of float, and one of them is total float, which we can simply call float in this class. Total float is the amount of time you can delay an activity, without delaying the project. If the total float is 0, that means the activity is critical, meaning it has no flexibility, so you must not delay it, or else the project will be delayed. Now, how do you calculate total float? You basically need to subtract the early start and the duration from the late finish. Some materials define total float as the late finish minus the early finish, but that is only correct if the network uses only finish to start logic. If the network includes other logic, such as finish to finish or start to finish, then that formula does not hold. For example, with finish to finish logic, an activity's finish may be delayed, causing the time between its start and finish to be longer than the required duration. For this class, please make sure you use the given equation. Let's apply the equation to this example, which has an early start of 2, a late finish of 7, and a 4-day duration. Then you calculate total float as 7 minus 2 minus 4, which gives you 1. You would then present total float on the PDM network by placing the total float between the early start and early finish. Another concept is free float, which is the amount of time you can delay the finish of an activity without affecting the early timing of any succeeding activity. This is different from total float, because with total float, you do not want to impact the final project duration, while with free float, you want to ensure you do not affect following activities. Calculating free float is a bit more complex, because it depends on the logic with the succeeding activities, so you must identify the successors of the activity by tracing the outgoing links from its finish. For finish to start logic, you calculate free float as the early start of the successor minus the early finish of the current activity, and then subtract any lag time. For finish to finish logic, you calculate free float as the early finish of the successor minus the early finish of the current activity, and then subtract the lag time. For instance, in this example, the free float of A, based on the finish to start logic from activity A to B, is 6 minus 3 minus 2, which equals 1, while the free float calculated from the finish to finish logic from activity A to C is 7 minus 3, which equals 4. Since you do not want to affect any succeeding activity, you take the smallest value, which in this case is 1. Alright, two other important types of floats are start float and finish float. Start float is the time difference between the late start and the early start of an activity. If the start float is 0, it means the start of the activity is critical. In other words, any delay in starting the activity would delay the entire project. For example, if the late start is 2 and the early start is 1, the start float would be 1. Finish float works the same way, but it applies to the finish side of the activity. It is the time difference between the late finish and the early finish. If the finish float is 0, we have a critical finish, meaning the activity must be completed on time or the project will be delayed. For instance, if the late finish is 6 and the early finish is 4, the finish float would be 2. If both the start float and the finish float are 0, then the entire activity is critical. However, if only one of them, either the start float or the finish float, is 0, the activity is considered partially critical. Alright, let's go back to example 2, which we did in the previous videos. So far, we've wrapped up both the forward pass and the backward pass, which means we've got the earliest start and finish times, as well as the latest start and finish times for every activity in the network. Now it's time to figure out the float times for each activity. We'll be looking at 3 types of floats: total float, TF, start float, SF, and finish float, FNF. Let's kick things off with total float. Total float tells us how much an activity can be delayed without holding up the entire project. The formula we use is total float equals late finish minus duration minus early start. You can think of it this way. We're taking the latest finish time, subtracting how long the activity takes, and then subtracting the earliest start time. Let's use activity A as an example. First, we grab the late finish from the bottom right corner. Next, we subtract the duration, that's the middle bottom value. And finally, we subtract the early start from the top left corner. So, for activity A, 3 minus 3 minus 0 gives us 0. This means there's 0 wiggle room for this activity. It's critical. In this class, we'll place the total float value in the top middle box of the activity node. Now, let's do the same for activity B. Total float equals 9 minus 4 minus 3, which works out to 2. Since the result is greater than 0, this activity has some flexibility. It's not critical. What about activity C? 13 minus 5 minus 6 leaves us with 2. Again, this activity has 2 units of float, so it's not critical either. You can follow the same method to calculate total float for activities D and E, as shown here. Next up, let's calculate start float. Start float measures how much flexibility we have on the start side of an activity. The formula for start float is start float equals late. Start minus early start. Let's break it down using activity A. We take the late start, bottom left value, and subtract the early start, top left value. That gives us 0 minus 0 equals 0. This means activity A has no flexibility when it comes to its start time. It's critical. Now, let's apply this to activity B. 3 minus 3 gives us 0. Since the start float is 0, the start of B is critical as well. What about activity C? 8 minus 6 comes out to 2. This tells us that the start of activity C can be delayed by up to 2 days without impacting the project timeline. Using the same approach, we find the start float for activities E and D to be 0 and 1, respectively. Now, let's move on to calculating finish float. Finish float represents the flexibility on the finish side of an activity. The formula for finish float is finish float equals late finish minus early finish. For activity A, we take the bottom right value, late finish, and subtract the top right value, early finish. 3 minus 3 gives us 0. This means activity A must finish on time or the project will be delayed. Here's something important to notice. Activity A has 0 total float, which means it's a critical activity. Since an activity is only critical when both its start and finish floats are 0, this confirms that both the start and finish sides of activity A are critical. Next, let's check activity B. Finish float is 9 minus 7, which works out to 2. This means the finish of B can be delayed by up to 2 days without delaying the project. However, as we found earlier, the start of B cannot be delayed. Since only one side is critical, we call this a partially critical activity. Now, for activity C, 13 minus 13 leaves us with 0. This means there is no finish float for activity C, making its finish side critical. This is another partially critical activity, but in contrast to activity B, it's critical at the finish, not the start. That means you can delay the start of C by 2 days, moving it from day 6 to 8, but you cannot delay its finish. Why? The dependency from the finish of activity E pulls the finish of C later, leaving no flexibility on the finish side. Finally, let's check activities E and D. Applying the same method, we find that both have a finish float of 0. And that wraps up the first part on float calculations. If you have any questions or need further clarification, feel free to reach out to us. Now let's move on to the second part, which is focused on critical path. Let's go over a few key characteristics of critical paths. First, a critical path is a path through the PDM diagram, where all activities are critical, either fully or partially critical. In other words, every activity on a critical path must have 0 total float, or 0 float on either the start or finish side. This means there's no room for delay. Any holdup will push back the entire project. Second, a critical path is the longest path through the PDM diagram from start to finish. Why is that? Well, since the activities on a critical path are critical, we can't delay any of them. These activities form the sequence that takes the most time to complete the project. So naturally, their total length ends up being the longest. Third, there can be more than one critical path in a project. When does this happen? It happens when 2 or more paths through the diagram have the same total duration and meet the criteria for being critical. In that case, all of them are considered critical paths. This means you'll need to keep an eye on multiple paths to avoid delays in the project. Finally, the length of a critical path represents the total duration of the entire project. Why? Because the critical path is the longest path in terms of duration, so its length essentially sets the timeline for the whole project. Let's go back to example 2, which we solved earlier. Now, let's find the critical paths in this network. First, we'll identify the critical activities. Fully critical activities are A and E because they have 0 total float. Partially critical activities, we have B, which is critical at the start, C, which is critical at the finish, and D, which is also critical at the finish. This means every activity in the network has some level of criticality, either fully or partially. To help visualize it better, let's mark the critical points on this network using these yellow boxes. Remember, a critical path cannot include any non-critical points. Now, let's identify the critical paths. To do that, we need to trace routes from start to finish that pass through critical points of fully or partially critical activities. One such path is A to start B, to entire E to finish C to finish D. Since this path includes only critical points, this is a potential critical path. To confirm, we need to check if its length matches the project duration. To calculate the length, we add the durations of activities that the path fully passes through, like A and E, and include lag times or subtract lead times between activities. For this path, A and E are fully on the path, so we add their durations. 3, A's duration, plus 8, E's duration, equals 11 days. Then we add the lag of 2 days from start B to start E and the lag of 6 days from finish C to finish D. This gives us a total length of 3 plus 8 plus 2 plus 6 equals 19 days, which matches the project duration. So this is indeed a critical path. Now, let's take a look at another path, from activity A to B to C to finish D. This path includes non-critical points, such as the finish of activity B and the start of activity C, so it is clearly not a critical path. Its total duration will be shorter than the overall project duration. To calculate its length, we add the durations of the activities fully on this path. 3 days for A, 4 days for B, and 5 days for C, which gives us a total of 12 days. Next, we subtract the 1-day lead time between B and C, giving us 11 days, and then add the 6-day lag time from C to D, resulting in a total path length of 17 days. As we suspected, this is shorter than the project duration of 19 days. Another path is A to E to finish, C to finish D. This path does not include any non-critical points, so it is a potential critical path. But we need to check its length. We add the durations of A and E, which are fully on the path. 3, A's duration, plus 8, E's duration, equals 11 days. Then we add the 6-day lag time from C to D, giving us a total length of 17 days. Again, this is shorter than the project duration, so this path is not critical either. The last path is from A to E to D. It is not a critical path, as it includes the start of D, which is a non-critical point. The total duration is 3 plus 8 plus 5, with no lag or lead, giving 16 days, shorter than the project duration. Alright, after checking all paths, only the first path, from A to start of B to E to finish of C to finish of D, is the critical path in the network. Any delays on the critical points of this path will extend the project duration. Alright, that wraps up this video on activity float and critical paths. Thanks for watching, and we'll see you in the next video. Goodbye for now.